Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to be talking about acid-base conjugate pairs. But before we do that, we want to briefly discuss which are our strong acids and which compounds are our strong bases. And I have this little kind of like setup here as far as the strong acids being in red, okay, and then the strong bases being in blue. I'll try to explain kind of what this means. Okay, so we're going to have hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric acid, and perchloric acid. We're going to have nitric acid and sulfuric acid. Okay, so if you look here, these are the things that I just stated online. These are your strong acids that I make my students memorize. Okay, and then the bases are just the elements here in blue. Okay, with their hydroxide. So if you look over here, here are all the alkali metals with their hydroxide, and then we work our way up on group 2 with just these 3. And there's a total of 8 strong bases that I have my students memorize. And you see how that comes in here and plays a role with acid-base conjugate pairs. Now there's also a couple definitions that I'd like to go over before we dive deep into the acid-base conjugate pairs, and that's the difference between an Arrhenius acid base versus a Bronsted-Lowry acid base, and really maybe even touch on the Lewis acid base definition as well. Arrhenius basically says that if you have an acid, it has to be something that increases the concentration of H+. Well, if you look at all of these acids over here, they all have H+ in them, so they would all qualify as an Arrhenius acid, okay? Same thing's going to be true for the bases, but it's going to be the increase in concentration of hydroxides. If you look, all these things have hydroxide, so all these things are going to be considered Arrhenius bases, okay? Now it's a very kind of restrictive definition, okay? So as they studied chemistry a little bit more, they wanted to be more inclusive. So the Bronsted-Lowry definition becomes more inclusive, and then the Lewis even becomes even more inclusive. So Bronsted-Lowry says an acid is anything that can donate a proton. So obviously, if it has hydrogen in it, it can donate a proton, okay? And then a base is anything that accepts a proton. Now, over here, all these hydroxides that have negative ions, okay, they can accept protons, okay? But there are other things other than hydroxide that can accept protons, okay? Maybe like a sulfide ion could act like a base and accept protons, okay? Maybe like carbonate would be another good one, or a bicarbonate, okay? Or even a substance like NH3, okay? Now, none of these have hydroxide in them, okay? So this definition that Bronsted-Lowry gives us is just a more inclusive definition, specifically with our bases in the types of things that might accept a proton, okay? And then the Lewis model talks about either accepting electrons or donating electron pairs, but that's going to be discussed in a future video, okay? So what I want to do is I kind of want to go through some of these acids and bases. Some of them are going to be strong, some of them are going to be weak, and talk about the ionization process and then this idea of acid-base conjugate pairs. So let me erase these definitions, and we'll talk about our first acid and what happens when you dissolve it in water, okay? Because that's going to be a big piece of our acid-base conjugate pair discussion, okay? So the first acid I'm going to take is HCl, and it's in this category of strong acids. And so when HCl is put into water, it's going to be a single arrow. Everything's going to push into creating ions of that, of the hydrochloric acid, okay? And when you get that, okay, if I was to do a particulate diagram of this, we would see a whole bunch of hydrogen ions with chloride ions, hydrogen ions, chloride ions, hydrogen ions, chloride ions. In fact, when this breaks up, there's going to be 0% of hydrochloric acid as a compound when you put it into water, and it's going to be 100% either hydrogen ions and chloride ions, okay? You don't see any HCl stuck together because this is considered a strong acid, okay? Well, let's do another one that has like a polyatomic ion. Let's do HNO3. That too is a strong acid, okay? So NO3, okay, is a strong acid. It's called nitric acid, and this too is going to go single arrow, and it's going to split up into its ions. However, the negative ion is polyatomic, okay? No big deal. It's still going to be 0% of the compound and 100% of its ions. So if we did a particulate diagram of this, it would look exactly like the hydrochloric acid, except instead of the chloride ions, it would be nitrate ions. So something like this. Here's my proton, here's my nitrate ion, here's my proton, here's my nitrate ion, here's my proton, here's my nitrate ion, okay? No HNO3 altogether because it too is a strong acid, okay? Well, what if I come in here and put HF, okay? Well, HF is not on my list of strong acids. And if it's not on my list of strong acids, it's considered a weak acid. And that becomes an important distinction between the previous two problems that I've done. So I'm going to label that as WA for weak acid. This is strong acid, this is weak acid. And if you have a weak acid, it goes into equilibrium, okay, with its ions. Okay, so the breakup kind of looks the same, but the split is going to be different. Okay, we're actually going to have a majority. Okay, and this is just an approximation. It does depend on the weak acid, but typically we'll say this is approximately 99% HF and approximately 1% the ions. So if we did a particulate diagram of this, it's going to look vastly different than our strong acids. We're just going to have a whole bunch of HF as a compound together, and then once in a while, it'll split up into its ions. Way different than the strong acid that we had before, okay? Now, let's get into this idea of an acid-base conjugate pair, okay? All of these things are acids because all of them have hydrogen in them, and they all can donate a proton. So that's kind of like what makes them an acid. So this is an acid, okay, but it's going to have a conjugate pair, okay? And the conjugate pair is going to be a base, so we call this an acid-base conjugate pair. And what the conjugate base is a substance that's present after the proton is donated. So as this hydrogen leaves the HCl, what's left over is the chloride ion, and that's called a conjugate base, okay? So the HCl and the chloride ion, not chlorine on its own, but the chloride ion is considered an acid and conjugate base pair. And we just continue that process here. For the nitric acid, this is the acid, okay? And then the substance that's present after the hydrogen leaves is going to be the nitrate ion. So nitric acid and the nitrate ion are acid-base conjugate pairs, okay? And the same thing down for here, okay? We get the HF and the fluoride ion. That's going to be an acid-base conjugate pair. Now, what you're going to find out is that conjugate bases tend to be negative ions. So I'm going to kind of write that down here. So conjugate bases, and I like to use this word tend because it doesn't mean always, but tend to be negative ions. Okay, now let's take a look at some of the bases, okay, and what happens. Okay, so here's kind of like my acids, okay. Let's talk about bases. So I got maybe a common one is going to be like sodium hydroxide. And what we're going to find out with sodium hydroxide is because it's a strong base, it's going to ionize 100%. So it's going to look something like this. So if I made a particulate diagram of this, we would get a whole bunch of sodium ions with hydroxide ions, sodium ions with hydroxide ions, sodium ions with hydroxide ions. There's no sodium hydroxide as a compound together. So 0% of this and 100% of the ions, okay? And if we do that one more time, but maybe something with two hydroxides, like a barium hydroxide, it's going to look something like this, a single arrow, because it's pushing completely all over to the product side, but we'll get two hydroxide ions for every one barium ion. So as far as a particulate diagram, make this a little bit larger so we can see everything. For every one barium that goes in there, we're going to have two hydroxide ions. For every one barium ion that I get in here, I'm going to get two hydroxide ions. But there's not going to be any barium hydroxide put together, okay? Now, what if we do something that's not on this list? Like, let's say something like magnesium hydroxide. If I do something like magnesium hydroxide, it's not on this list, so it's not a strong base like these other two. And since it's not on this list, we're going to call it a weak base. Okay, so we're going to use an equilibrium arrow to say that it's weak. Okay, and as far as the rest of the equation, it's going to look similar. However, because this is weak and because the K value is going to be small, okay, we're going to have almost all of this be reactants, okay, and very little bit of it will actually ionize. These are just approximations, okay. So if we had a particulate diagram of this, okay, most of it would be magnesium hydroxide as a compound. So there's a magnesium hydroxide, here's a magnesium hydroxide, here's a magnesium hydroxide, and then every once in a while, you'll get a magnesium ion, and for every one magnesium ion, you're going to get two hydroxide ions. So there's a hydroxide ion. I'll put the second one up there. So this would be a good particulate diagram of what magnesium hydroxide would look like, okay? Well, this has some acid-base conjugate pairs as well, but this time we're starting out with base, okay? So all of these are bases, okay? They all have the ability to accept protons because of the hydroxide ions, okay? However, okay, the substance that's present, okay, without the hydroxide are going to be these positive ions, okay? And these are going to be considered conjugate acids, okay? So the conjugate acid of sodium, barium, and magnesium are all considered conjugate acids of these bases, okay? So up here, okay, if you will, sodium hydroxide and the sodium ion is an acid-base conjugate pair, okay? Here's our base, and here's my conjugate acid, okay? Same thing here. Here's the base, here's the conjugate acid. So barium hydroxide and the barium positive 2 ion are considered an acid-base conjugate pair. And finally, the magnesium hydroxide and the magnesium positive 2 ion, okay, are considered acid-base conjugate pairs, okay? So if you look here, all these conjugate acids, they tend to be positive ions, okay? So let's go ahead and write that down. Conjugate acids tend to be positive ions, okay? Now, what becomes interesting is that we have this kind of like perspective of these acid-base conjugate pairs as far as their strength is concerned, okay? And I wish I had a little bit more room on the board, okay? So I'm going to kind of just maybe squeeze it in between these two. And the way it works, okay, as far as strength, okay, you have this top portion of the chart that's going to be what we call strong, okay? And then this big part in the middle, which is called weak. And then there's this third part, and we call that negligible. If I can spell, negligible. And negligible means it's terrible. It doesn't even work, okay? So if you have something that is something that's strong, okay, and it's super high, then its conjugate is going to be in that negligible category, okay? So remember, there's three categories. So if you're strong, the conjugate's going to be negligible, okay? If your acid is negligible, then the conjugate is going to be strong, okay? So and then of course if you're weak, it's just kind of like this inverse relationship, okay? But if you have like a weak acid, its conjugate is going to be weak as well. And how weak it is depends on how weak, okay, the acid is. So let's take a look at the examples that we have on the board, okay? We have hydrochloric acid, okay? That is considered a strong acid, okay? That means its conjugate base is going to be in the negligible category. And its conjugate base is the chloride ion. And what that means is the chloride ion as a base is terrible at accepting protons, okay? That's why this reaction works in this direction. This chloride can never, ever pick up a proton to make the hydrochloric acid. This reaction does not work in reverse at all. So that's what makes this conjugate base super, super terrible, where it belongs in the negligible category, and that's because its acid is strong, okay? Now for HF, it's weak, okay? So its conjugate base is going to be in that weak category as well. Now, how weak it is depends on how weak the acid is. If it's a super, super weak acid, then its conjugate is going to be one of the stronger conjugate bases, okay? So it's kind of like this inverse relationship that exists in this weak category, and the weak category is very, very big, okay? And you'll have this inverse relationship, okay? The strong acid and strong base category actually is really, really small. It's just this portion, okay, of the scale, which means its conjugates, it's going to be on the opposite end. It's going to be small as well. So this category is small, and this category is small, where the weak area is very, very large, okay? Now let's take a look at our bases, okay? Sodium hydroxide is considered a strong base, so it's way up here, which means its conjugate is going to be way down here. So sodium ions, okay, the conjugate acid, it's a terrible acid, okay? It's not strong at all. In fact, it is like one of the worst acids that's possibly out there, okay? Now, where that's different is if we had something like magnesium hydroxide. Magnesium hydroxide is a weak base, okay? So its conjugate, the magnesium ion, is also weak, okay? Now, depending on how weak this is will determine how weak this is, but they're both going to be a part of this weak area, and everything is dictated by the value of the equilibrium constant, okay? And that's true for both of these. And just to let you guys know, we've been talking about K sub C and K sub P in the previous videos. Now that we're talking about acids and bases, okay, this K value, because this is an acid, it's going to be called Ka. And because this is a base, this is going to be Kb. And what you find out is that those Ka and Kb values will tell you what part of the weak scale are you on, okay? So the larger the K value, the stronger the weak acid is, okay? So if HF is a pretty strong weak acid, okay? So it's a weak acid, but it's one of the stronger ones. So it might be up here. Well, then the fluoride ion would be at the bottom if that was the case, okay? So once again, we have this inverse relationship between the acid-base conjugate pair If you are a strong acid or a strong base, then your conjugate is going to be negligible, okay? If you are a weak acid or a weak base, then your conjugate is going to be weak as well. And remember about that inverse relationship that exists. So in this video, you have to do two things. The first thing is just be able to identify what an acid-base conjugate pair is, okay? And then the second thing is saying, hey, if I have a strong acid, then the conjugate base is going to be negligible. But if I have a weak acid, the conjugate base is going to be weak. And then the same is true for the bases. If I have a strong base, the conjugate is going to be a negligible acid, okay? But if I have a weak base, okay, the conjugate is going to be weak as well, okay? We are going to continue this conversation about strong acids and weak bases as we do ice charts for these weak acids and weak bases, and also introduce this idea of pH. Those things will be discussed in future videos. If you like this content, please like and subscribe. And when you add that comment, it really does push this information out to other students that might be interested in learning chemistry.